Hi everyone, welcome back. Let me explain again about this topic 2. It is about the primitive of graphics programming. It means it is about all the fundamentals and the concepts of graphics programming. Now, this subject we are going to use OpenGL and OpenGL ES as our graphics program. And this topic 2 is divided into 4 different parts. The first part, which we have seen in the previous lecture, it's about the OpenGL pipeline, whereby you see a sequence of steps that OpenGL requires to take when they do a rendering operation. Now, it is a very general pipeline, and most of the graphics programming can actually use this pipeline to perform the rendering operation. And in part 2, we are going to dig in further. I'm going to introduce you to the OpenGL, the traditional approach. Alright, and there are also modern approach which will be discussed in part 3. So let's move on to topic 2, part 2, which is the introduction to OpenGL in the traditional approach. The contents for this topic 2, part 2 consists of the functions, some available libraries, the basic OpenGL syntax, the naming conventions, some data types, and also the others. Again, OpenGL and OpenGL ES belongs to the general programming packages, and OpenGL is used in the desktop, while OpenGL ES is used in the embedded platform. OpenGL ES is the subset of OpenGL. As we have seen in the previous lecture, the OpenGL pipeline consists of the fixed function pipeline and the programmable function pipeline. And I have actually grouped them into traditional approach and modern approach respectively. So today, we are going to look at the traditional approach, which is the fixed function pipeline for our OpenGL. What is OpenGL? Well, OpenGL is a software interface to graphics hardware. Now, GL stands for Graphics Library. It allows you to create interactive programs that produce color images of moving three-dimensional objects. It can also control computer graphics technology to produce realistic pictures or ones that depart from reality in imaginative ways. So as you can see, OpenGL belongs to the general purpose graphics package, and it provides user with a variety of functions for creating and manipulating pictures. Now, these routines can be broadly classified according to whether they deal with the graphics output, input, attributes, transformation, viewing, subdividing pictures, or general control. Now, the basic building blocks for pictures are referred to as graphics output primitive. They include character strings and geometric entities such as points, straight line, curved lines, filled color areas, usually polygons, and shapes defined with array of color points. In addition, some graphics packages provide functions for displaying more complex shapes, such as spheres, cones, and cylinders. Routines for generating output primitives provide the basic tools for constructing pictures. Besides that, attributes are the properties of the output primitive. That is, an attribute describes how a particular primitive is to be displayed. This includes color specifications, line styles, text styles, and area filling patterns. Now you can change the size, the position, or the orientation of an object within a scene using geometric transformations. Now some graphics packages provide an additional set of functions for performing modeling transformations, which are used to construct a scene where individual object descriptions are given in local coordinates. Such packages usually provide a mechanism for describing complex objects, such as an electrical circuit or a bicycle with a tree structure. Other packages simply provide the geometric transformation routines and leave the modeling details to the programmer. After a scene has been constructed, using the routines for specifying the object shapes and their attributes, a graphics package projects view a picture onto an output device. Viewing transformations are used to select a view of the scene. It is the type of projection that's going to be used and the location on the video monitor where the view is to be displayed. Other routines are available for managing the screen display area by specifying its position, size, and structure. For three-dimensional scenes, visible objects are identified and the lighting conditions are applied. Interactive graphics applications use various kinds of input devices, including a mouse, a tablet, and a joystick. Input functions are used to control and process the data flow from these interactive devices. Some graphics packages also provide routines for subdividing a picture description into a named set of component parts, and other routines may be available for manipulating this picture components in various ways. Finally, a graphics package contains a number of housekeeping tasks, such as clearing a screen display area to a selected color and initializing parameters. We can lump the functions for carrying out this course under the heading Control Operations. Many other computer graphics programming libraries have been developed. Now, a package called OpenInventor furnishes a set of object-oriented routines for describing a scene that is to be displayed with calls to OpenGL. The Virtual Reality Modeling Language, or in short, VRML, which began as a subset of OpenInventor, allows us to set up three-dimensional models of virtual world on the internet. We can also construct pictures on the web using graphics libraries developed for the Java language. With Java 2D, we can create two-dimensional scenes within Java applets. For example, we can produce three-dimensional web displays with Java 3D. With the RenderMan interface from the Pixar Corporation, we can generate scenes using a variety of lighting models. Finally, graphics libraries are often used in other types of systems, such as Mathematica, MATLAB, and Maple. Now, let's take a look at the basic OpenGL syntax. Function names in the OpenGL basic library, or we call the OpenGL core library, are always prefixed with GL. And each component word within a function name has its first letter capitalized. The following example illustrates this naming convention. GL begin, GL clear, GL copy pixels and GL polygon mode. Now, as you can see, we always use GL as the beginning, and the first letter after GL always capitalize. The second one, now, certain functions require that one or more of their arguments be assigned a symbolic constant specifying, for instance, a parameter name, a value for a parameter or a particular mode. Now, all such constants begin with the uppercase letter GL. In addition, component words within a constant name are written in capital letters, and the underscore is used as a separator between all component words in the name. The following are a few examples of several hundred symbolic constants available for use with OpenGL functions, as you can see in these examples. The OpenGL functions also expect specific data types. For example, an OpenGL function parameter might expect a value that is specified as a 32-bit integer. But the size of an integer specification can be different on different machines. To indicate a specific data type, OpenGL uses special built-in data type names such as GL_byte, GL_short, GL_int, which is GL integer, GL_float, GL_double, and GL_boolean. Now, each data type name begins with the capital letter of GL, and the remainder of the name is the standard data type designation written in lowercase letters. Some arguments of OpenGL functions can be assigned values using an array that lists a set of data values. This is an option for specifying a list of values as a pointer to an array, rather than specifying each element of the list explicitly as a parameter argument. Now, in addition to the OpenGL basic or core library, there are a number of associated libraries for handling special operations. Now, the OpenGL utility, GLU, provides routines for setting up viewing and projection matrices, describing complex objects with line and polygon approximations, displaying quadrics and B-splines using linear approximations, processing the surface rendering operations, and other complex tasks. Every OpenGL implementation includes the GLU libraries, and all GLU function names starts with the prefix GLU. Now, to create a graphics display using OpenGL, we first need to set up a display window on our video screen. This is simply the rectangular area of the screen in which our picture will be displayed. We cannot create the display window directly with the basic OpenGL functions, since this library contains only device-independent graphics functions, and window management operations depend on the computer we are using. However, there are several Windows system libraries that support OpenGL functions for a variety of machines. The OpenGL Utility Toolkit, GLUT, provides a library of functions for interacting with any screen windowing system. These library functions are prefixed with GLUT, and this library also contains methods for describing and rendering quadric curves and surfaces. In general, a parameter that affects the way a primitive is to be displayed is referred to as an attribute parameter. Some attribute parameters, such as color and size, determine the fundamental characteristics of a primitive. Other attributes specify how the primitive is to be displayed under special conditions. Examples of special condition attributes are the options such as visibility or detectability within an interactive object selection program. Here, we treat only those attributes that control the basic display properties of graphics primitives without regard for special situations. For example, lines can be dotted or dashed, fat or thin, and it can be also blue or orange. Areas might be filled with one color or with a multi-color pattern. Text can appear reading from left to right, slanted diagonally across the screen, or in vertical columns. Individual characters can be displayed in different fonts, colors, and sizes. One way to incorporate attribute options into a graphics package is to extend the parameter list associated with each graphics primitive function to include the appropriate attribute values. A line drawing function, for example, could contain additional parameters to set the color, width, and other properties of a line. Another approach is to maintain a system list of current attribute values. Separate functions are then included in the graphics package for setting the current values in the attribute list. To generate a primitive, the system checks the relevant attributes and invokes the display routine for that primitive using the current attribute settings. Some graphics packages use a combination of methods for setting attribute values, and other libraries, including OpenGL, assign attributes using separate functions that update a system attribute list. A graphics system that maintains a list for the current values of attributes and other parameters is referred to as a state system or state machine. Attributes of output primitives and some other parameters, such as the current frame buffer position, the foreground color, or the background color, are referred to as state variables or state parameters. When we assign a value to one or more state parameters, we put the system into that particular state, and that state remains in effect until we change the value of a state parameter. So, we define OpenGL as a state machine because everything shall remain until you explicitly change it. It has a global state that can be changed in lots of different ways. For example, certain settings like GL depth test, GL blend can be enabled or disabled using the function GL enable or GL disable. Now, depending on the OpenGL state, certain operations might behave very differently. Because of this, it is important to be careful about managing OpenGL state during the execution of your program. There are two strategies for this. First, you assume nothing. When writing a function that uses OpenGL, consider that the state could be anything. Explicitly set the values of the state parameters you depend on. The second strategy that you might use is default configuration. You can decide on a set of reasonable default state values and set the state to these values at the start of your application. Anyway, you change one of the state parameters, restore the parameter to its previous value after you are done rendering a component of a scene. This is about the naming convention. As I mentioned in the previous slides, it begins with a lowercase of GL if you are using the core OpenGL library. You can use the prefix of GLU if you are using the OpenGL utility library. And if you can write GLUT if you're using OpenGL Utility Toolkit. And then followed by the purpose of the function, and you have to write it in uppercase for the first letter, alright, as shown in this example. Now, GL color is from the core OpenGL library, and this function is actually to specify the drawing color. While for GL vertex here, it's also from the core OpenGL library. It is used to define the position of a vertex. Here, you can see a simple OpenGL command. GL, again, is from the core OpenGL library, and vertex is a function which is used to draw a vertex, followed by 3FV. Now, 3 here is the number of components. If you put 2, it represents X and Y. For 3 is X, Y, and Z. Alright. Now for this case, F is representing the data type that you are going to use. F here means floating point. So it means that your parameters in this function, you have to use floating points. If you put an I here, it means here the attributes or the parameters here must be integer. The third part of this command, V, is represent the vector. Now without the V, it means it's a scalar, and you can have different kind of data types in OpenGL, which is defined in the core OpenGL library. You can use assigned integers, unsigned integers, floating point numbers, boolean, size, and enumeration. Don't forget to declare your constant with the uppercase separated with underscores. Apart from all this, there's one function that you should know as well, which is the initGL function. Now this function is meant for carrying out one-time OpenGL initialization tasks, such as setting the clearing color. Now this function will only invoke once in the main function. And then there's another function called display function. This function is known as a callback event handler. Now, an event handler provides a response to a particular event, such as key press, mouse click, or window paint. This function display is meant to be the handler for the window paint event. The OpenGL graphics system calls back display function in response to a window paint request to repaint the window. For example, when your window first appears, it will call this function, or when your window is restored after minimize, or even when your window is resized. Alright, this function display will be called. Callback means that the function is invoked by the system instead of called by your program. The display function runs when the window first appears and once per subsequent repaint request. Observe that we included OpenGL graphics rendering code inside this display function, so as to redraw the entire window when the window first appears and upon each repaint request. GLUT provides high-level utilities to simplify OpenGL programming, especially in interacting with the operating system, such as creating a window, handling the keyboard, and the mouse inputs. So as you can see from this table, these are some examples of the command that you can use from this GLUT library. And an event queue is a repository where events from an application are held prior to being processed by a receiving program or system. Now, GLUT main loop function puts a program in an infinite event loop. In each pass through the event loop, GLUT will look at the events in the queue. For each event in the queue, GLUT will execute the appropriate callback function if one is defined, and if there is no callback is defined for the event, the event will be ignored. These events including when you resize your window, when you click the mouse, when you move your mouse, or when you press a keyboard, alright? Or even if the situation is idle. Now we use GL color function to set the foreground color and GL clear color function to set the background color. In OpenGL, an object is made up of geometric primitives such as triangle, quad, line segment, and point. A primitive is made up of one or more vertices. OpenGL supports the following primitive: the point, okay, GL lines, line strip, line loop. Now, the difference between these two is that the ending point will always connect back to the starting point because it's a loop, okay? And you have your GL polygon, GL triangles, GL triangle strip, GL triangle fan. Now for this primitive, it always connect back to the starting point. So it will form like a fan. And then we have GL quad and GL quad strip. Now a geometric primitive is defined by specifying its vertices via GL vertex command or GL vertex function, enclosed within GL begin and GL end, as you can see from this example. Now, GL begin specifies the type of geometric objects such as GL points, GL lines, GL quads, GL triangles, and GL polygon. For types that end with S, right, you can define multiple objects of the same type in each GL begin or GL end pair. For example, if you use GL triangles because there's a S, each set of 3 GL vertex defines a triangle. The vertices are usually specified in float precision. It is because integer is not suitable for trigonometry operation. Precision of float is sufficient for carrying out intermediate operations and render the objects finally into pixels on the screen. Double precision is often not necessary. So in this example, a quad, 4 vertices, and we set the color to be red. This is the GL color 3F. All subsequent vertices will have the color of red. So once you set once, alright, above this statement, all these points will get affected. It will become red. So if let's say you use GL quads, okay, in your primitive, you have to specify 4 vertices, right, the position for that quad. The following diagram shows the OpenGL 2D coordinate system, which corresponds to the everyday 2D Cartesian coordinates with origin located at the bottom left corner. The default OpenGL 2D clipping area is an orthographic view with X and Y in the range of -1 to 1, with the center at the origin. The clipping area is mapped to the viewport on the screen. As you know, viewport is measured in pixels. Try to study this example to convince yourself that the 2D shapes created are positioned correctly on the screen. Okay class, I would like you to do an experiment. Open up a paint, draw anything that you like, and try dragging the corner of the paint window. Either you make it bigger or smaller. Observe that all the shapes are distorted. Now, we can handle the resizing of window via a callback handler called reshape function, which can be programmed to adjust the OpenGL clipping area according to the window's aspect ratio. I will actually show you during the lecture. Now the clipping area actually refers to the area that can be seen or can be captured by the camera, and it is measured in OpenGL coordinates. While for viewport. Viewport is actually refers to the display area on the window or on your screen, which is measured in pixel in screen coordinates. But you have to exclude the title bar, okay? Now, besides all these features that we have seen, we also can certain object transformation. For example, translation, rotation, and scaling, all right, to adjust or to define the location of our object in the workspace. And other features consist of animation, all right, you can perform animation, for example, rotating the shape via the GLUT pose redisplay function. And also you can do a double buffering. Now, double buffering actually uses two display buffers to smoothen the animation. The next screen is prepared in a back buffer, while the current screen is held in a front buffer. Once the preparation is done, you can use this glut swap buff command, alright, to swap the front and back buffers. Now with the timer function, you can call back at the specific fixed interval. You can also register callback functions to handle keyboard inputs for normal and special keys, respectively. Similarly, you can also register callback function to handle the mouse click and mouse motion. Now during the lecture, I will actually demo a simple code that exhibits the OpenGL program using the traditional approach. Alright, all these, they are using fixed function pipeline. And I would like to take this opportunity to acknowledge all the references that I have been using to prepare the contents for this topic 2, part 2. And the code for this topic is don't be shy about asking for help. It doesn't mean that you are weak. It only means that you are wise. What we have learned in this part 2, what we have learned in this topic 2, part 2, is that Open Graphics Library is a cross-language, cross-platform application program interface for rendering 2D and 3D vector graphics. And also we have seen some characteristics or the basic concept of traditional approach for OpenGL. If you think this video is useful, don't ever forget to like and subscribe to my channel. I'll see you again in the next video. Stay safe, stay healthy, and stay connected. See you. Bye.